Hey, welcome back to Abstract Algebra. In this section, section 4.2, we're going to take a look at some elementary properties of rings. So you can see the goals of the lecture are written there. I want to establish some of these elementary properties. In particular, I just want to look at the author's lemma 4.2.1. Then I want to look at how cancellation laws work in rings. They requires a certain property, so we'll look at cancellation laws in integral domains. And then we're going to end by proving that every finite integral domain is actually a field. All right, so this is just some chance for us to practice using our new language and get used to some of the structure in this ring theory business. So let's get going here. Here I've written out a statement of the lemma 4.2.1, but I haven't written the proof of it yet. So we're just going to kind of walk through each one of these properties in order. So I'll let the preamble be in the statement of the theorem itself. So we have some ring called R, and we have a couple of elements in it. Remember, by 0, I always denote the additive identity, and when I write dashes in front of things, it means the additive inverse. So this first property is saying that when you multiply anything by the additive identity in a ring, you get the additive identity. Okay, so here's how we're going to prove that. We choose an element in our ring, and we want to look at what A times 0 is. Well, the additive identity is, among other things, equal to itself plus itself. 0 is 0 plus 0. And then I can use the distributive laws. The left distributive law in particular, A times 0 plus 0 is A times 0 plus A times 0. And if I just sort of reorganize that equation by just writing the extreme left and the extreme right, then in the additive group R under addition, this element, A times 0, is equal to it plus itself. So I can cancel additively in the additive group R, right? We have cancellation laws work in a group. I can cancel this element from both sides of that equation. And when I do that, I'll get 0 on the right, and on the left, well, I get A times 0. So that proves one of the two things that I wanted to show. It proves that 0 is A times 0. I'm going to leave the other one to you. You show that 0 times A is 0, and you'll use the right distributive law. Okay, so there's a proof of part A. When you multiply something by the additive identity in a ring, you get the additive identity. Anything times 0 is 0. What's part B say? Let me get rid of my annoying highlighting. Part B says, I mean, you can look at it. You can look at what it says, and you might be looking at it going, well, yeah, of course that's true. Those are the rules of signs I've used my whole life. But this is an abstract statement. So if I just kind of decorate it as I talk, it says that if you take an element A, oops, sorry about that. It says if you take an element A and you multiply it by the additive inverse of some other element B, well, you get the additive inverse of A times B. And this other thing just says, well, you could have put the inverse on A. So basically, what part B is saying is that when you multiply an element by the additive inverse of some other element, you get the additive inverse of the product. All right? So in other words, those usual minus sign rules that you're used to work. Okay, well, to prove something like that, take our elements A and B and R. I guess I'm writing it again. I said I wouldn't. The statement has the nature, it claims I know what the additive inverse of an element is, right? It's saying that the additive inverse, watch when I underline this, the additive inverse of AB is A times minus B, A times the additive inverse of B. So we can test that. Somebody claims to know what the additive inverse is. Okay, well, let's just try it. Let's take AB and add to it this thing A times minus B. If we get 0, then A times minus B must be the additive inverse of AB. And you can probably already see what I'm going to do. I'm going to use the distributive law, but I'm going to do it kind of in reverse. We usually call that factoring. Yeah, so I get A times B plus minus B. Well, that's A times 0, and we just proved that A times 0 is 0. So technically speaking, I should also show, oh, I ran out of room here. I should also show that A times the opposite of B plus AB is equal to 0. Well, there I'll just distribute again on the left. Minus B plus B is still 0. Yeah, so there. That's not the whole thing. I proved one of these two inequalities, or equalities rather. I'm going to leave this one to you. But the same exact idea, you just add that thing, minus A times B to AB, and show that you get 0. All right. Let's see. I ran out of room. I was going to prove part C and part D. I guess I'm going to just leave them as exercises. The author has written proofs of them, but part C is really just two applications of B. Yeah, I mean, if you wanted me to just speak it out loud, if you take that opposite of A times opposite of B, well, that's the, yeah, you can just use part B twice, and then remember that the additive inverse of the additive inverse is the element. So you can check out Herstein's proof or ask me about it. I'm just going to move on. Same thing with part D. Part D, just add -1 if 1 is unity. Add -1 times A to A and show that you get 0. You'll use the distributive laws. Cool. All right, so I wrote proofs of these two. I alluded that you can look at Herstein, or you could try to prove these two yourself. Try to prove them yourself. I'll bet you can prove it. It's fun. Okay, so what's my second proposition? My second proposition, this is not a theorem in your book. It's actually taken from one of the exercises, but let's see what it says. So if you take a ring, R, and I'm going to suppose that it has no 0 divisors. You can watch the video before this one or ask me in class, but I'll remind you a 0 divisor is a non-zero element that multiplies by some other non-zero element to give 0. So this ring has none of those. It has no 0 divisors. And then I could say the condition that R has the left cancellation law. So what do I mean by that? If you take 3 elements, one of them A not 0, and AB is equal to AC, then B is equal to C. So even though A might not be a unit, A might not have an inverse, you can still left cancel it. This is just the name of this proposition. Would be the left cancellation law in rings with no 0 divisors. There's also a right cancellation law in rings with no 0 divisors. Okay, let's try to prove this. So let's take our ring and let's take our ingredients. So we've got this A, B, and C. They're in our ring. A isn't 0. The product of A and B and the product of A and C are equal. Okay, well, working in the ring, that means that AB minus AC is 0, which is the same as saying that A times B minus C is 0. Okay, but our ring has no 0 divisors. A is not 0. Its product with B minus C is, so B minus C has to be 0. R has no 0 divisors. Yeah, well, if B minus C is 0, then B is equal to C. So I could left cancel that element A, even though A doesn't have an inverse. I didn't prove it by multiplying by the inverse. I don't know A is a unit, but I didn't need to have an inverse. It follows from the fact that there's no 0 divisors. And again, you can check out the right cancellation law. You can give the exact same proof. Okay? So if your ring has no 0 divisors, like for example, if it's an integral domain, the integral domain, you remember, is a commutative ring with unity that has no 0 divisors, then you have a cancellation law. Or if your ring is a field, every element is a unit, there's no 0 divisors in a field, you have the cancellation law. Cool. All right, I'll leave the right cancellation law to you. What's the second proposition? The second proposition is basically the converse. It says if you take a ring that has the left cancellation law, So if whenever A isn't 0 and AB is equal to AC, that forces B to be C, then your ring actually cannot have 0 divisors. So these two propositions together basically say that, having the cancellation law is equivalent to having no 0 divisors. That's kind of what it means. Okay, well, let's see if we can prove this. This is kind of an important proof technique. If you want to show that something can't be a 0 divisor, here's one way to do it. Let's let A and B be two elements of the ring R. Let's suppose that A isn't 0, but we'll suppose that the product of A and B is 0. All right, then what I want to convince you of, if I'm trying to show that R has no 0 divisors, I want to show that B is 0. If we can show from that assumption that B is 0, then it will follow that this ring has no 0 divisors. Okay, well, how are we going to do that? AB is equal to 0. We proved above that that would also be the product of A and 0. Yeah, so if we write that equation in one line to focus on it, it looks like we have the product of A and B is equal to the product of A and 0. And our assumption about this ring, when the product of A and B is equal to the product of A and something, you can cancel the A's. Yeah, so B is equal to 0 by our property, by our hypothesis. And that shows that A cannot be a 0 divisor. A was an arbitrary non-zero element of the ring, so our ring has no 0 divisors. Okay, so having no 0 divisors is equivalent to being able to cancel. So for example, in the ring of integers, the ring of integers is not a field. Elements don't have multiplicative inverses in general, but you can still cancel. If you gave me an equation in the integers like 2 times x is equal to 2 times y, then I can say that x is equal to y. And I'm not deriving that by multiplying by the inverse of 2, because in the integers, 2 doesn't have an inverse, but I can still cancel. Cool. All right. So we've reached the final proposition. I wanted to show you that every finite integral domain is a field. I think this is an interesting fact. I think it's a cool proof, but really I'm including it here to kind of give you a chance to understand some of our terminology. Okay. So let's let R be a finite integral domain. So let me unpack that term. So first of all, finite means there's a finite number of elements in it. Integral domain means it's a commutative ring with unity. So R is equal to, say, well, we know there's an additive identity. And then we have a bunch of other elements. Let me just call them A1, A2, up to say AN. So I'm just specializing off for the 0 element there, is a commutative ring with unity. It has no 0 divisors. That's what an integral domain is. An integral domain is a commutative ring with a 1, a multiplicative identity, and it is devoid of 0 divisors. Okay? We want to show that R is a field. Well, what's a field? A field is a commutative ring with unity in which every non-zero element is a unit. Yeah, so we've already got the commutative ring with unity part, so it suffices to show that every non-zero element of R is a unit, that every non-zero element has a multiplicative inverse. So let's let R star be the set of non-zero elements. right? So I already carved out 0 up here and then called the rest of the elements A1, A2, and so on up to AN. So R star is just the non-zero elements. In R. And choose an element A in R star. And I want to show A is a unit. Okay, well, let's multiply everything in R star by A. So we form the set A times A1, A times A2, and so on. A times AN. Oops. A times AN. So I multiply everything in R star by A. So I claim no two of those elements are equal. Because note, if A times AI is A times AJ, well then AI is equal to AJ by the cancellation law, right? This integral domain has no zero divisors, so we have a cancellation law. So that means that this set, let me just give it a name here. That set also has n elements. No element in that set is 0. A times AI is not 0 for all I, because A isn't 0 and AI isn't 0, and this ring has no zero divisors. Yeah, so that means that S is a subset of R star. Every element in S is not 0, and it has the same size as R star, so S is actually equal to R star. So when I've multiplied the elements of R star by one of its fixed elements, A, I don't know which AI is, it's one of them, I just end up getting the elements in R star back. I've permuted them. Right? But this ring, this integral domain, it's where did we write it? It's a ring with unity. Unity is never 0, right? So the unity element belongs to R star. So it belongs to this set S. So there has to be some index I such that 1 is equal to A times A sub I. Yeah, because 1 belongs to R star, which is equal to S. So one of these elements, I don't know which one it is, but one of them has to equal 1. 1 is in there somewhere. And well, if A times AI is equal to 1, that means that A is a unit. AI is its inverse. Cool. So I hope that you liked that. It gives you a chance of practicing this vocabulary: unit, unity, integral domain, field. So rewind it, watch it again, ask me some questions about it as you're digesting this stuff. All right, see you soon.